Welcome to Conversations from St. Norbert College, a program that encourages good discussion in our community on today's local and global issues. Now, your host for Conversations from St. Norbert College, author, professor, and nationally known sports economist, Dr. Kevin Quinn.
Welcome to Conversations from St. Norbert College. I'm Kevin Quinn. Our special guest is Kathy Licht, and we'll discuss the future of science in higher education, Licht's research and career path, as well as her time spent at St. Norbert College. Licht is a 1992 graduate of St. Norbert, an associate professor of earth sciences at Indiana University, Purdue University, Indianapolis. She's been researching the Antarctic ice sheet and joined St. Norbert professor of geology, Tim Flood, on a research expedition there last January. Kathy, welcome to the show.
Thank you.
Well, of course, I'm going to have to ask you about your time at St. Norbert, but let's start first with your work in Antarctica. What's interesting about Antarctica?
Well, I would say what's not interesting. It's a beautiful, beautiful continent, and the geology there is largely hidden by the ice sheet, and so we have to use some interesting tools to try to figure out how to access all of the rocks that are hidden below the ice sheet. And the ice itself is a fantastic recorder of climate changes over time, and we know it's responding to climate changes, and so it's an ice sheet similar to one that covered this area about 20,000 years ago, and so it's a modern analog for something that doesn't exist in places that used to exist in places like Wisconsin.
Well, I guess the next question is why should we care? I mean, other than just it's an interesting intellectual endeavor, but you know, the average person who's watching this, why should they care about what's going on at the South Pole?
Well, the main reason is that all of the ice that's tied up in the ice sheet has the potential to contribute to sea level rise. And we know with things like Superstorm Sandy that really impacted the coast, that costs the country a lot of money. So from an economic standpoint, there's a lot of reasons to be concerned when we have millions of people living at sea level, and sea level is on the rise, and we'd like to know how much will Antarctica really contribute.
Well, you're a geologist, meaning you are interested in rocks. I think most of us think that the pole is just covered with ice. Is that the case? Do you have to drill through the ice to get to the rocks, or are there just rocks laying around?
Yeah, Antarctica is an extremely large continent. Most people think it's that space on the bottom of the map that's either not there or it looks massive. It's about the size of the continental U.S. and Mexico combined. And so if you imagine that area and you fill that all up with ice until only the peaks of the Rockies are sticking out, that's one way to visualize what Antarctica looks like. So most of it is flat and white, and in places there are rocks that are exposed that we can study.
So what particular work do you do there? I mean, what's interesting to you about the rocks that are there?
Well, we like to use them as a tracer for the ice, and so if we'd like to know how the ice sheet behaved in the past, how big did it get during the last ice age, how quickly does it retreat, how does it respond to climate change, we need a way to trace that when the ice is no longer in those positions. So what we do is use rock types that are distinct from different parts of the continent, and then we can trace those sort of like tracing a trail of breadcrumbs, and say, oh, well, the ice from over here must have extended in this area because it took granite with it and dropped it along the way. So we can use the rock types to learn about the ice sheet history.
So you can actually tell how old these rocks are and when they were placed in certain spots, is that right?
Yeah, those are sort of two different questions, and I'm going to try to get you to think like a geologist and say, well, the rock might have formed 500 million years ago, but it was transported only 20,000 years ago. So there are lots of different kinds of questions we can use. What are the rocks that were carried by the ice sheet that we can't even see exposed today? So those deposits left behind give us some clue as to what's buried under all that ice. And then if we can understand when those deposits formed, we can learn about the ice sheet on top of it.
So how do you tell how old a particular rock is? I mean, there's no markings on it or anything like that.
Right, there are plenty of geology jokes, which I'll spare you. One of the tools you can use are a variety of radioactive elements, such as uranium, that occur naturally in lots of different kinds of rocks. So in one case, there's a mineral called zircon, which forms in things like granite, and it forms naturally with some radioactive uranium in it. And over time, that uranium decays to lead, and we can measure the ratio of those two different isotopes, or those two different elements, and from that calculate the age.
Is that work that you do there, or do you mostly gather the rocks and then bring them back to your lab at home or wherever and test them there?
What we do is collect the rocks in Antarctica and box them up, and they get shipped back. Sometimes it takes 4 months until we see them again, and then we prepare the materials in Indianapolis, but we don't actually have a lab to measure the uranium and lead materials, and so we go to the University of Arizona. They have a facility there where we can measure the samples.
Sounds warmer than the South Pole.
Yeah, ironically though, the lab is kept so cold we have to have a heater on. It's 100 degrees outside in Arizona, and there's a heater on in the lab.
Well, let's talk about the station, the research station that exists. It's McMurdo, right? Is the big place, and I think that most of us have some idea that it exists, but really don't know a whole lot about it. So tell us a little bit about the station itself and what is life like there.
McMurdo Station is very much like a small town in Wisconsin in a lot of ways. There are
a lot of churches and bars.
There are 3 bars, 1 church. There's a library. There used to be a bowling alley. Unfortunately, that building is no longer safe to be inhabited. There are places for people to live. There are shops. There are computers. There's an ATM. So
ATM.
Yeah, you have to buy, get your money someplace to buy things at the bar and other places. So it's a small town. It gets up to probably 11 or 1,200 people in the maximum population in the Antarctic summertime. And so there's a group of people who are hired to make the town, run, and so they hire people from all around the country to do all of the jobs that need to be done. And once that infrastructure is set up and the people are there to learn their jobs, then the scientific groups come down and rotate all throughout the Antarctic summer season. And there are chemists, biologists, physicists, atmospheric scientists, as well as geologists who come in to do their research projects there.
And it's an international effort, is that correct?
The McMurdo Station is a U.S. base, and so it primarily houses U.S. researchers. Occasionally there are groups from other countries that come in, scientists who use a facility, and when there are search and rescue efforts, it certainly becomes an international endeavor.
So there's a contractor that runs the thing all year round, and then it sort of has a high season like Cape Cod in a sense, right?
Exactly.
So how many people are there all year round?
In wintertime, I think there are about 150 people or so that stay winter over. So they maintain the basic functions, so you can actually start it up again in the springtime. And then in about September, early October, they bring the vast majority of those contractor folks back to get everything spun up so the science can really start in October.
So how do you get there? I mean, you can't take a boat because it's over land, right? And do they have an airstrip, I'm guessing?
Yeah, it's an interesting thing. You fly down to New Zealand, and from New Zealand down to Antarctica. There's a passenger terminal. Your bags have to go through screening just like they would in the normal airport. And you fly down, and the first time I went, I thought, landing a large plane on ice doesn't seem like a very good idea. It turns out it's a snow-covered runway that's groomed, and some of the planes that go down are ski-equipped, and some have wheels, and you can land that way. And the main U.S. base is actually sitting on the edge of an active volcano, and so there is land exposed, so the buildings sit on land, but the airstrips are made on the nice flat ice surface.
Really? So are you restricted in how much luggage you can bring, or
Yes.
is that part of the grant, I guess, that you write to get down there? Or?
Yeah, so there is a weight restriction on how much baggage you can bring, but for scientific gear you can get exceptions, and people send large amounts down for big projects.
Can you bring nail files on the plane? Or?
I think you can do a nail file. For a while they were iffy about knives.
Really?
Yeah.
I would imagine that there's a lot of equipment that you're going to want to take with you there that probably wouldn't make it onto a U.S. Airplane.
That goes checked bag instead of carry-on.
And so you live in dorms when you're down there, right? Are they like college dorms? Are they more like, apartments?
They're mostly like college dorms. So most of the buildings, there's a line of buildings that are 4 stories, and in most cases there are 2 bunk beds in the room, and so you may know the person you're bunking with, you may not. For those of us who are sometimes there just for a week or 2 at a time, we're the transients, and so you come and make your little home there and use the group bathroom facilities and all of that, just like a dorm.
Just like a dorm. Except you guys are there to really work hard. I think maybe that's not always true of college students.
Oh, now.
So what was your biggest surprise when you got down there? Just as far as the creature comforts and that sort of thing.
That's a good question.
What did you miss most?
What I miss most is milk.
Milk?
Yeah, that's the one thing that they have reconstituted milk. So that's the one thing, coming from the dairy state.
I was going to say, you're true to your Wisconsin roots.
Yes.
And now you actually did some work outside of the base, right? You actually went camping in a sense, right?
Yes.
What's camping like in that environment? Is that like ice fishing?
It's less fancy than most ice shacks in Wisconsin, I think. You just use the standard tent. I mean, you get strong tents, mountain tents that you would buy here in whatever shop, and you just have to make sure they're staked down well, and you put snow around the edges so they don't blow away. The other kind of tent we use is called a Scott tent, which is basically if you see a big sort of bright yellow a tent it's a classic sort of icon of Antarctic exploration, and that was used in the early 1900s, and we still use the same design because it works so well when the weather gets really horrible.
Have you ever been caught out in some bad weather? Well, what is bad weather there, and have you ever been caught in it?
I have not been caught in anything really horrible. We had some really cold, windy days where the wind chill might be 70 or 80 below, and you're trying to collect samples. That's not so much fun, and we tried not to be out under those conditions. People have had some really harrowing experiences with hurricane-force winds, picking up snowmobiles and tossing them across the ice sheet. So I'm glad I didn't experience that,
wow.
But it has happened.
How cold does it get in the wintertime, their wintertime?
The coldest temperature ever recorded is in the middle of the East Antarctic ice sheet. It was at a Russian station, and it was minus 128 degrees Fahrenheit. No wind.
No wind. Well, thank God for that.
Yeah,
right?
I know. It's without the wind chill.
Well, let's talk a little bit about the work that you do and how it relates to global climate change. And it's become a political debate in this country, unfortunately, to me, rather than a scientific debate. What's your perspective on that? I mean, where does what you do fit in to the modern debate about man-made warming?
Well, I would say there's no debate in the scientific community about man-made warming for starters, and so I agree with you that it's unfortunate. It has become political. It should be something we all care about because we live on the planet, and so it's unfortunate that the concern has gotten away from what's happening and what can we do about it to denying that change is even happening. So the way my research fits in is because there's a big concern about sea level in particular, that we'd like to know how much is Antarctica going to contribute, for instance. And so as a geologist, I can say, based on the rocks I find and the kinds of deposits, this is how big the ice sheet was, and this is how quickly it retreated. And then the people who make computer models of ice sheets then can put that into their models and say, here's an actual data point you can use to test the model to see if your predictions work, to see if your model actually works. So we really provide a foundation for testing the models that predict what Antarctica will do in a warming world.
There's a lot of work going on down there just about this. I know that they drill these cores that it's really cool, and then they measure the gas bubbles that are trapped in the core, and they can tell quite a bit about what the world was like, 10,000, 20,000,
850,000
850,000 years ago. And I mean, it must be really neat to be part of that forefront. I mean, this is new knowledge.
It is really exciting, and I think the ice cores produce some of the most interesting records we have in science in a lot of ways, because it really is a fantastic recorder of climate changes over time, and it's relatively constant. And so, the snow falls down year after year and compresses into ice, and so you build up this extremely long record, and the snow traps air bubbles into it, and so you can extract those gases and measure CO2. So if you wonder if people say that CO2 is high and it's going up, how do you know that? What's your perspective? It turns out we have an 850,000 year record showing the natural climate cycles over time. It shifts between 180 parts per million during glacial cycles, and then usually up to 280 parts per million during warm periods or interglacials. So it's sort of this natural rhythm or heartbeat of the planet. So 180, 280, 180, 280, and now we're up to 400. And you can map that out with population and industrialization, and it's really happened in the last 150 years or so.
So something like, what, 60% of the fresh water on Earth is trapped there, is that right? And how much of that is likely to melt, and what will that do to sea levels? And why would we care?
Yeah, if you melted all of Antarctica, which is unlikely, you would raise sea level over 200 feet. And I always joke with my students in Indiana that that would make southern Indiana almost oceanfront property. So bye now. No. What we think the most vulnerable places are the Antarctic Peninsula, which is the little tip that points up towards South America, and the West Antarctic ice sheet. And if those areas would melt, sea level would potentially come up on the order of, 10 to 15 feet or so. And that New Orleans is already below sea level, so for them it's extremely relevant. For New York City, I think they were quite surprised during Superstorm Sandy that the storm surge really inundated areas they didn't expect. So it's not just the rise, but then it's everything else that happens in the ocean that really causes problems with flooding. And, for us here in Wisconsin, you might say, well, we're far from the coast, why does it matter? Well, it probably matters to your insurance rates. It matters to how we help out our neighbors on the coastal areas, how we should be planning, how we should be thinking about designing this country, but it also matters to small island nations in the Pacific. They have the potential to lose their whole country. And so they have been thinking hard about what will we do? Will we lose our language? How will we stay together? Do we want to do that? Where will we go? And so for those people, it's an even harder problem to deal with.
Well, one of the issues is that it's the rich countries that are contributing the most because they have the largest economies, they're burning the most fossil fuels, but they're the ones either least likely to be affected by this or have the capacity to mitigate it in some fashion. I mean, if Charleston looks like it's starting to go underwater, we have the capability of building a seawall.
Yes.
But little places in Micronesia don't have that way of doing that. And I mean, I agree with you. I think that this is something that is likely to define the next 100 years, I think, of human existence, is how we deal with that. I'm not sure that a lot of folks really understand how quickly the climate can change. You grew up in Wisconsin. I'm guessing that you studied a little bit about that. Tell us just a little bit about the glacial history here in the state of Wisconsin.
During the last ice age, so roughly about 20,000 years ago, we sort of use a broad brush term, but it's a good time frame. We know that there were ice sheets that covered most of Canada, and they extended down into Wisconsin. Didn't cover the entire area. Many people have heard of the driftless area in the southwestern part of the state, but it really shaped the landscape. So the shape of the land surface is the way it is, largely because the ice sheets covered the area. And one of the great benefits is the wonderful fertile soil that it provided for all of the farming activities here. So the ice sheet retreated relatively slowly at times, but we know ice sheets, and including those in this area, can retreat quite rapidly. And so the ice sheet retreat and climate are closely linked, but you can have climate shifts, but sometimes it takes the ice some time to respond because they're such a massive feature.
So 20,000 years sounds like a long time, but it's really almost within the stretch of human history. Not quite, but almost.
Yeah, I mean, geologically it's a drop in the bucket, so we always joke, well, that's so modern, a lot of geologists don't, 20,000 year time scale isn't even relevant for some of the things we do, but, because it shapes the way we interact, or it shapes the landscape and it affects how we interact with it, it really does matter, and we know that the ice retreated in a few thousand years, and we know that massive climate changes have happened over the scale of decades. So those have happened naturally, and they're really hard to predict. And so one of the challenges with climate change are the unpredictable parts. They're sort of the long-term changes that we understand, and then we can look in the geologic record and say, but there are periods where unpredictable things happen on a quick time scale. Now what happens if we superimpose that on a climate system we don't really understand as we go forward with higher CO2 than we have seen in the last several hundred thousand years?
For example, the Gulf Stream is sort of an artifact of the sea atmosphere situation, but that could change. I mean, it could shift.
The
like
Gulf
this.
Stream is not constant.
It's
right?
not constant. It could change very quickly, and that would have a profound impact on the weather in the United States. And by the time that happens, by the time we even realize it, it would probably be a little bit too late.
Yeah, some of the Earth systems are so big, it's hard to conceive that we could actually change them. But all of the data we have shows us that is indeed what's happening. And once you change really big systems, it's hard to get them back to the state that you're used to.
Well, I'd like to talk a little bit about your thoughts about science education. That to some degree, it's under fire in this country. That when I grew up in the 60s and 70s, we worshiped science. I mean, we put people on the moon, and we did all these really cool things. And even up until the 80s and the 90s, when we were doing genetic modification. I mean, we could change the world with science. What, in your opinion, has happened in the last 10 or 15 years? What do you think is going on? And how do you think that's going to affect us in the future?
That's a really interesting question. You could spend a long time talking about that. But I think one of the issues is accessibility of information. And so if anybody can look up anything, then all of a sudden anybody can be an expert on any topic. And I think, and I'm sure that it's not just science, but in a lot of areas that we sort of lose sight of the depth of understanding people have in certain areas and how that shapes their ideas and opinions and interpretation of information. So I can show somebody a graph and say, oh, well, look at this, and try to convince you, but there's lots and lots of supporting information behind that. So I think it's important to understand that this availability of information is a real blessing, but it's also a real challenge to try to help students and the informed citizen really understand how we get to scientific information, or how we get scientific information, and how we can use it appropriately.
Are we losing sight? Generally not scientists, but is the public losing sight of the scientific method and as a philosophy and what that means to understand something that way?
I think there probably is some aspect of that. In this day and age, we like instant gratification, and you can look stuff up and get information, but there's a whole philosophy of science, as you say, that you can't prove anything is true. You can disprove lots of things, but to actually prove something is true is something that many philosophers have said, you just can't do that. You can't go back 20,000 years and be here when the ice sheet was here. And so all we can do is use evidence and make arguments based on the evidence that we have. And it's a more subtle way of thinking than the 10-second news clip with the answer.
Wikipedia is great and it's horrible.
Yes.
And as an economist, I can appreciate that. I tell my own students that you're not arriving at the truth with a capital T necessarily,
right.
But we call it a discipline because you go through a disciplined series of procedures to try to understand something. And in the end, our human brains have a comprehension of it that's enhanced and very nuanced, very analog rather than digital about something because we've gone through the act of trying to understand that. Well, let's talk about your own education. After you left St. Norbert, you went to Boulder, and I've been lucky enough to be at the Center for Atmospheric Research there for a little bit. It's one of the most beautiful places on Earth. If I were going to put a research place, I'd put it there.
Excellent choice.
So what attracted you to Boulder?
I was interested in studying glaciers, and so I looked at programs around the country that had glacial geologists who I might be able to work with. And that rose to the top as one of the great choices, and I was accepted to work there. So it was really a lot of luck, and my advisor at the time taking a chance, I didn't obviously come from a large research institution, but because I had done research here at St. Norbert, I think he said, oh, well, here's somebody maybe worth taking a chance on.
It certainly is a different place. Northeastern Wisconsin and Boulder, Colorado are very different places. So now you're originally from Wisconsin, right? Barron,
yes.
Wisconsin, if I'm not mistaken. Why did you choose St. Norbert?
I've thought about that quite a lot, and I think I came on a campus visit and was really impressed. It was, beautiful campus. Everybody was extremely friendly and supportive, and it seemed like a place that I would be comfortable for for starters, and I think that's really important for, for students. You can't learn and really be part of the community if you don't feel comfortable there.
That's true. I mean, we like to think that we're doing more than just, what's in the classroom, although that's really important, but
Right.
You're around other people that are roughly, the same age, and the people that work here are cognizant of that. So what do you remember most about your time here that you can talk about on the air?
Yes, good caveat there. No, I think one of the things that I really appreciated was all of the opportunities outside the classroom. Whether it was doing geology field trips, we went to some fantastic field trips to Central America, or I also went with one of the groups down to Chicago over a spring break and volunteered at schools. And so I think it was all of those, in addition, of course, to the wonderful classes, but it was all the extra opportunities that made it a really rich experience.
So what advice would you give for somebody who is thinking about being a scientist, not necessarily a geologist? Is that advice different if they're male or female, or are we past that now?
I would like to think we're past that. In geology, we have usually at least half the students are women, whether it's at St. Norbert or at IUPUI. There are a lot of women involved in the field. And so, I think it comes down more to personalities rather than gender at this stage. And I think, if you're curious about the world and you're willing to work hard and ask questions and really, make a lot of queries into how the world works, then science is really fun. I mean, geology is like being a detective where you don't have many clues. And so different sciences suit personalities differently.
I think you have to be of a certain personality to be a geologist. You have to, seriously, you have to love working in the field and not necessarily in the most comfortable environments. There's a lot of lifting.
Yes, a lot of hoisting rocks.
Rocks are heavy,
yes.
as it turns out, and moving them around is tough. If we think about just the vast array of different kinds of minerals, stones, etc., I mean, we walk by them every day. Mm-hmm. And if you actually pick them up and look at them, it's incredibly complex. I mean, things that are made of the same chemicals can have vastly different appearances because of the way that they were formed. How do you go about thinking and cataloging all of that kind of stuff? I mean, it's almost impossible, it seems.
Yeah, I mean, it is. It can be extremely overwhelming. And so, you start with the big picture. In order to sort of draw people in and to get yourself started, say, well, what can I wrap my head around? What stage am I at? And for starters, it's usually visual appearance. We're attracted to rocks and stones and gems that look visually appealing to us. And so you can gain an appreciation just at the visual level. But if you decide you want to pursue it further, then you can get down to the chemical level, to the bonding level, physics. All of that is part of it. And one of the things I think that most geologists really appreciate is that we really get to draw on all the sciences. So on a daily basis, I deal with chemistry. Probably some of my projects certainly deal with biology and physics as well. So geology is really an integrated science that really allows us to think about the whole world, which is a lot of fun.
Well, a lot of folks choose geology as if you're an English major or something like that, as their one science course. Why do you think that is? And what do you hope they leave your class with, knowing that they're probably never going to take another science course?
Well, I did that. I came as a business and psychology double major, and I took one geology class and went, this is fantastic. I have to be a geology major. And honestly, that's the way most geology students come to the field. And so, what I hope is that we will draw in those people who had a latent interest and didn't really know much about geology and show them that it's a fantastic career option. But for those who maybe don't want to follow that path, to appreciate the natural world around them and say, what are the natural processes that happen on the Earth, and how can we make smarter choices about how we live on this planet because we know this information?
Well, what's next for you? I mean, are you going back to the McMurdo, or
that
what are you doing next?
Remains to be determined. I've got several research proposals that I'll be submitting in about 2 weeks, and so those will go through the review process. And if any of them are funded, they all include trips to Antarctica to collect more samples. And so come back to me in 9 months, or hopefully that ought to do it, and I should have an answer to that.
Well, everyone I ever met that went down there couldn't wait to go back. So there must be something that's really appealing about the experience. And unfortunately, we're out of time, but I want to say thank you very much for sharing that with us and for coming back to campus. I know that you're going to be speaking to a group of our undergraduate scholars, and I'm sure they're going to get quite a bit out of the talk. I hope you've all enjoyed our show. Until next time, I'm Kevin Quinn. Best wishes for good conversations from St. Norbert College.